In this video, we want to take a look at the model for current in a conductor. A true description of the microscopic processes of the flow of charge in modern electronics requires an understanding of the atom and the atomic nature of the universe. And this would require us to have more advanced physics, in particular quantum mechanics and solid-state physics. Many of the interesting properties of the way that you can buy electronic devices and why you have such power at such low cost is because of the power of this type of physics. Electrical engineers can control the properties by doping semiconductors to change the property from a pure conductor to a pure insulator over 40 orders of magnitude, and they're changing their resistance, a quantity that we'll learn about in a future video. And of course, if you really want to be able to build devices, you could get a degree in electrical engineering, or if you really wanted to push the envelope and build the most advanced stuff, of course, a degree in solid-state physics. Now, that type of advanced math and more advanced stuff we don't have in this course, so we're going to restrict ourselves to something which we can do classically with the background that we have, and that's we're going to look at metal conductors. And in metal conductors, we can treat the electrons flowing through it in a more classical approach with less complicated physics. In short, we can think of them much like we think of a gas, and we have some experience dealing with gases. So that's the goal here, is to try to build us a microscopic view of current and what's going to lead us to an opposition to current called resistance. So we're going to start out with kind of this model. The outer electrons in a good conductor, say a metal, are very weakly bound. Okay, so we're not talking about the inner electrons. We're talking about the ones that are at the outside that are less tightly bound, the so-called conduction electrons. And in a metal, they basically are so weakly bound that you can think of them as kind of setting a set of atoms like this. The electrons kind of freely can go between the various metals. They're not tied to any one particular atom itself. Instead of dealing with the individual atoms, we'll just talk about them as if they're sitting like atoms in a gas. So I'm going to think about this. This is a random motion of an ideal gas. Now, we may say that there's no net motion, but the fact is that the atoms inside a gas are going in all directions at all times. So they're going around like this. They're not sitting still. But when you sum up all that motion, you find that there's no net motion. So there's no net motion, but there certainly is microscopic motion of these atoms. In the same way, inside a metal, the electrons are moving all around between the various atoms. But they're disorganized and random. And so the net sum of all their velocities taken into account is zero. So there's no net charge motion. Now, if you take the gas and you were to put a plunger on the end of it, and you were to apply a pressure and push that plunger, then you would still have these atoms moving in random directions, but there would be a net push and hence a net velocity component causing these atoms to move to the right. They'd bang into each other and not go in a straight line, but the net effect is that they would have a net motion in this direction. So when we talk about the motion of the gas, we're talking about the part that's not random, that is the net effect when you sum everything up. And this is in the direction of pressure. So pressure is what causes the flow. The velocity or the movement of the gas is the flow. In our circuits, the push is provided by the voltage. So the voltage is like pressure. The voltage creates an electric field, which applies a force. And the net effect is, if these were positive charges, that they moving would be slightly disturbed so that they would have a small net component to the right. They wouldn't all go to the right. Some would still go in various directions. But the net effect is there's a net flow, a net charge flow to the right. We call this a current. So there's always motion of the electrons. The voltage simply gives them a net motion in one direction, and that direction of positive charge flow is what we call current. Now, microscopically, we can try to build up some sort of a model. So let N be the number of charge carriers per volume. Let this VD be the average net, and we'll just call it speed for the minute. So it's often called a drift velocity or drift speed. Q is the charge on a carrier, and A is the cross-section. The amount of charge that moves in one direction depends on the number of carriers, that is the number of charged objects, whether that be electrons, atoms, or what, and the charge per carrier. Using the things we have up here, that's the number of carriers per volume times the volume. And then times the charge per carrier, which we'll call Q. Now the volume is N. We get N is the charge number of carriers per volume. The volume is the area A times some delta X. So what I'm doing is I'm looking at some area A and some delta X that these carriers have moved through. And then times Q. But delta X would be equal to the speed times delta T. This is back from mechanics. In essence, we're saying not accelerated, moving at a constant velocity, then V delta T is equal to delta X. We put that up in here, and we get N times A times this V drift times delta T times Q. Bringing that down, we have the definition that the current is defined as delta Q over delta T. But I can take my formula for delta Q right in here and divide out the delta T. And I get number of charge carriers per volume. I get the charge per carrier, the drift velocity, and the area. This is the equation in the textbook. Now, usually we define the current per area, and this is called the current density. So current density is defined as I divided by A. If we divide both sides by A, then we get that the current density is the number of carriers per volume, the charge per carrier, and this drift speed or drift velocity. Now it turns out that the material that you have, different materials, usually have a certain number of carriers per volume, and between different metals this doesn't change too much. They also usually have the same charge. They'll have like one free electron, and that charge will be the charge of an electron 1.6 10 to the minus 19 coulombs. But they can have substantially different drift velocities. So if you want a very high current density material, you want something with a high drift velocity. And so scientists and engineers either try to create by mixing materials or to find a material with a high drift velocity if they want to be able to have a high current. Now, at the microscopic level, it is possible that the drift velocity will not be the same in all directions. For instance, you might have a material like a crystal, and the crystal, the atoms may be bound pretty tight in one direction a lot more than in another direction. Same thing in polymers and such. So if we use this model for something other than a pure metal, it might be difficult for the electron to go in one direction, so it has a very low drift velocity, and a much faster drift velocity in another direction. If that's the case, we can put vectors on this. So put a vector on the current density and the velocity, drift velocity here, and that will give you an ability to make this into a vector and have different values in different directions. This is usually not seen at this level, of course. Although it is occasionally. Let's give an example of such a problem. What is the magnitude of the drift velocity of an electron in aluminum if 5 amps of current flow through an aluminum wire of area 4 times 10 to the minus 6 meters squared? You can assume each aluminum atom provides 1 electron. First is to find N. N is equal to 1 charge per atom, and I need the number of atoms. To find the number of atoms, I know I have a density of 2.7 grams per centimeter cubed, and that the gram molecular weight of aluminum is 27 grams per mole. I have 6.02 times 10 to the 23rd atoms in 1 mole. Put those in and you get 6.02 times 10 to the 22nd carriers per centimeter cubed. Now, to find V, this is just equal to I divided by A in Q. So I have 5 coulombs per second. I have 4 times 10 to the minus 6 meters squared times 100 centimeters per 1 meter squared times 6.02 times 10 to the 22nd centimeters to the minus 3 and also 1.6 10 to the minus 19 coulombs. You put all that in and you get 0.13 millimeters per second, or 130 microns per second. So the drift velocity is not very big. This is true. It's not the electron that flies all the way from the switch to the light to make it light up. It's the disturbance in the field that does. All right, we'll talk more in the next video.